In section 9.6, we're going to finalize all the tests concerning testing for an infinite series to be convergent or divergent. In this section, the last two tests we're going to look at are the ratio test and the root test. Okay, with these last two tests, by far the most important test, especially concerning some upcoming uses of it later in Chapter 9, will be this ratio test. The root test, while important, definitely doesn't garner as much attention as this ratio test, as this is something we're going to use pretty much the rest of this chapter. So we're going to kind of focus on that a little bit. But before we kind of jump into what the ratio test is, how do we test for absolute convergence? Well, if you remember from 9.5, we tested for absolute convergence only for an alternating series. But what if we wanted to know if any series was converging absolutely? Well, the first thing we'd have to realize is that the terms would have to be approaching zero very quickly. If you recall that idea of the speed of a series, for something to be converging absolutely, the terms of that series would have to approach zero very quickly. So the answer to the question here is we're going to need to use the ratio test. Anytime you want to test for absolute convergence, or just in maybe specific cases where other tests don't really work so well, this ratio test is going to be the way to go. So what does this ratio test tell us to do? Well, it's kind of in the title. You're going to have to set up a ratio or a fraction, and that fraction is right here. What we want to do is set up a fraction of a sub n plus 1 over a sub n, and I'll talk about what that is, but that's the ratio we'll set up. We'll take the absolute value of that, and what we're doing is finding the limit of that ratio. If the limit of that ratio is less than 1, then we say the series converges absolutely. If that ratio is greater than 1, then we say the series diverges. And if we see that the limit of that ratio gives us a 1, then that means the test is inconclusive, but really as a follow-up, it really means you shouldn't have used the ratio test. It probably meant you should have used probably one of the comparison tests or something like that. So those are the three outcomes. Again, I'll talk about how this fraction gets set up, but really we're just taking the limit of this fraction as n goes to infinity, and again, if that number we get is less than 1, converges absolutely. If it's bigger than 1, then the series diverges. Okay, so that's really all there is to it. So I think the big thing we have to talk about here is what is the ratio that we're setting up. Well, the first thing we have to talk about is in the bottom of the fraction, we have a sub n. A sub n is just the general term of your series in the problem. So like you see in this example over here, let's say I have a general series term of n cubed over n factorial. Of course, I guess the problem would be rewritten as this. We'd have the summation notation and all of that. But that's not what we're really focusing on. We're not focusing on the summation notation. We're focusing on the general term of the series. So that's what, in this example, the general term is. Our general series term is n cubed over n factorial. So then what would be the next consecutive general term? That's what this is right here. It's asking you to write the next term after the general term. And of course, the next term over would be a sub n plus 1. So what that's telling you to do is to plug in n plus 1 wherever you see an n. And this is going to be the key, and I would make note of this. Anytime you plug in n plus 1, it needs to be in parentheses. That's kind of the number one mistake that people will make when they're doing this, is that anytime you plug in n plus 1, that needs to be done with parentheses. As long as you do that, then the next consecutive general term, or that's just a fancy way of saying a sub n plus 1, that is just going to be, in this case, n plus 1 all cubed over n plus 1 all factorial. So as long as you can handle setting up this fraction, then these problems really aren't too bad. So let's go ahead and take a look at this ratio test. Here we're going to apply the ratio test to a problem we don't need to use the ratio test on. And I hope you can see this is really just equal to 1 to the n over 5 to the n. And if you remember the little trick here, we can rewrite that is 1 over 5 to the n power, which is just a geometric series with r equals 1/5. And of course, since r is equal to 1/5, that's less than 1, so we know the series converges. But let's go ahead and use the ratio test just to kind of verify that. So how do we set up this ratio? Well, what is the next term over from 1 over 5 to the n? All we need to do is plug in n plus 1 wherever we see an n. So on the top of this fraction, we'll have 1 over 5 to the n plus 1, and in the bottom of this fraction, we'll have just the original general term of this infinite series. Of course, we want to put an absolute value around that, and we're taking the limit as n goes to infinity. We've seen this many times already in this chapter. When we're dividing by a fraction, we take that bottom fraction and multiply by the reciprocal. The other thing we need to realize, and we saw this in 9.5 concerning absolute convergence, when we apply an absolute value, what's going to happen? Well, in this case, there's no alternating pieces, so we don't really have to worry about this absolute value. All the terms are positive, so we can just remove the absolute value symbol. So I kind of did those two steps in one. I took that bottom fraction and multiplied by the reciprocal, so we get 5 to the n over 5 to the n plus 1. And I'm also dropping off the absolute value because all of this is positive and there's no alternating parts, so we don't really need the absolute value. Okay, so we need to take this limit. Right now, we really can't do that unless you realize that in the bottom we can simplify. We can take that plus in the power and make it two separate things being multiplied. 5 to the n times 5 to the 1. And of course, that really worked out nicely because those 5 to the n's cancel, and we're just left with 1 over 5 to the 1 power, or just 1/5. And when we take the limit of a constant, we get that same constant. So careful, that's not really the final answer here, but what we want to do is take that answer and interpret it. Since we got a number that is less than 1, we know because of this ratio test that this series converges absolutely. And again, we need to state what test we used. So we're going to say that the series converges absolutely by the ratio test, which we already knew, but we're now kind of verifying that because, of course, this was a geometric series. Okay, so now let's do a problem where we don't know the answer ahead of time. We have this series here, and we're going to apply the ratio test to it. How do we know that the ratio test is appropriate here? Well, I hope you can kind of take away something that we know. This problem isn't like 9.5. There is no alternating series here. In 9.4, we needed a comparison. Well, if you notice, there's nothing really we can compare this to. We have what looks to be like a geometric thing in the top, but it's not really. And then we have like a little p series here in the bottom. There's really nothing we can compare this to. Certainly we can't use the integral test because we can't find this integral. So really the ratio test is kind of the Swiss Army knife, so to speak, of these tests. It kind of has everything built into it, and for the most part, it's the one that you can use a lot of the time. Okay, so let's go ahead and set up our ratio. We're going to use this ratio test. In the top of the fraction, we're going to have 4 to the n plus 1 over n plus 1 all cubed. Again, we're plugging in n plus 1 wherever we see an n, and again, when we do that, we're using parentheses. So again, we'll have 4 to the n plus 1 over n plus 1 all cubed, and then we divide by just the regular general term, so that's why that's in the bottom. We're going to put an absolute value, and of course we're taking the limit of that fraction. Again, like with basically every one of these problems that you're going to see, we need to multiply by the reciprocal of the bottom fraction. And on top of that, in this particular problem, again, there are no things that are ever going to be negative, so we can just remove that absolute value without having to worry about it. So in the top of the fraction, we'll have n cubed, because again, we're flipping this fraction, so n cubed will go to the top with the 4 to the n plus 1, and then the 4 to the n power stays in the bottom of this overall fraction. So just be careful with your fraction simplifying skills here, and now we can attempt to take this limit. Of course, it's kind of a mess right now, so we should try to go ahead and simplify what we can. And in the top of this fraction, we can simplify the 4 to the n plus 1. 4 to the n plus 1 becomes 4 to the n times 4 to the 1. And that worked out really nice again because those 4 to the n's cancel. And now we're left with this. If we take this limit, we'll end up with some sort of n cubed polynomial in the bottom. And of course, when we take that limit with the top, those n cubes would cancel, and we're just left with a limit value of 4. What conclusion can we draw here? Well, since our ratio, the limit of the ratio, I should say, is greater than 1, we can say that this ratio, this infinite series diverges by the ratio test. Again, very important that we put what test we used to say or to come to the conclusion that we came to. Okay, so here we have a few more examples of the ratio test. And in this first problem, just kind of as a standard way we're going to approach these infinite series, the good news is if you ever see a factorial in your infinite series, you're going to want to use the ratio test to test that series to see if it converges or diverges. So kind of if we just follow that rule of thumb here, then we'll kind of be ready to go with regard to these types of problems. So let's go ahead and set up our ratio test. In the top of this fraction, we need to set up the next consecutive general term. And the way we do that is we just plug in n plus 1 wherever we see an n. So we're going to have 3 to the n plus 1 all over n plus 1 factorial. And again, use parentheses when you plug in n plus 1, or you could find yourself kind of already setting up these problems incorrectly. In the bottom of the fraction, we divide by the original infinite series general term. Again, kind of 2 steps in one like I've been doing in the first 2 problems. We can flip that bottom fraction, and we can also drop the absolute value. In this particular problem, I'm going to leave it just so we can kind of analyze it for needing to be dropped, but I think you guys can maybe see we can drop that right away. It's not incorrect to always leave it, but if you can drop it off, it's usually a good idea to drop off that absolute value because it's just one less thing to write. In addition to that, these are really the problems where I don't want to flip that bottom fraction and kind of combine that all into one fraction. That kind of gets a little bit messy. So what I'm going to do is multiply by a separate fraction. Instead of making this one gigantic fraction, it might be a little easier just to take that bottom fraction and flip it as just this separate fraction. And again, we're multiplying now since we're using the reciprocal. Okay, so once we do that, we're ready to try to simplify this, and what we need to do is review something back from 9.1. Even though 9.1 really wasn't an AP test kind of section, there were several things we went over that kind of got us ready for infinite series. One of those things was a review of simplifying factorials. So here's your quick double review, so to speak, of simplifying factorials. Recall that a factorial is just telling you to take whatever you see next to the exclamation point and multiply that by each next term 1 less. So of course 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1, or 5040. But that's not really what we're doing here. We're trying to simplify one of these factorials with n in it. So if we have an n plus 1 factorial, if we wanted to simplify that, we would say that the first thing we'd have to be multiplying by is n plus 1. And then we would multiply by 1 less than that. Of course, 1 less than n plus 1 would just be n. And if we wanted to keep on going, of course, 1 less than n would be n minus 1. And depending on where you stopped, that last term would still have a factorial on it. And I'm just stopping right here for the sake of doing this little example. So when we come up here to our problem at hand, there's 2 things we can simplify. We can simplify this piece, and we can simplify this piece. Of course, the top of that fraction will be 3 to the n times 3 to the 1, like you've seen in the last 2 examples. And in this bottom part with the factorial, we're going to stop right away with that next term over. We're going to write n plus 1 times n factorial, because you'll notice that n factorial in the top can cancel with the n factorial in the bottom. The 3 to the n in the top cancels with the 3 to the n in the bottom. And once we do all that, now we're left with a nice and easy limit to take. Of course, now I'm going to drop off the absolute value like I mentioned earlier, but we could have done that back at that first step. But now we're ready to take the limit. 3 over n plus 1 as we go to infinity is equal to 0. And again, as long as we get a number that's less than 1, and certainly 0 is less than 1, we can come to the conclusion that our infinite series up here converges absolutely by the ratio test. Okay, in this next example, again, it's a great candidate to use the ratio test because it's got a factorial in it. So let's jump straight to doing that. We're going to set up the ratio. In the top of this fraction, be careful. There's a lot of n's here, so again, wherever we see an n, we're going to plug in n plus 1 using parentheses. So we're going to have n plus 1 all to the n plus 1 power over n plus 1 all factorial. And then, of course, luckily in the bottom of the fraction, we're just going to rewrite the original general series term. After that, like you've seen in every one of these problems, we're going to take that bottom fraction and multiply by the reciprocal. Again, I'm not going to write this as one big fraction. I'm going to write it as two separate fractions being multiplied. Just like you saw in this last example here, there's two things we can simplify. We have this n plus 1 in the power right here, which we can of course split up into two pieces. And then we can of course simplify this bottom factorial so that maybe we can cancel with the other factorial in the second fraction. So let's go ahead and do that all in one step. We're going to take the top of the fraction, so it'll be n plus 1 all to the n times n plus 1 all to the first power. And in the bottom, with the factorial, we're going to stop right away at that second term over. We're going to have n plus 1, and then we're going to subtract 1 from that, which would be n, and that's where we want to stop expanding, or simplifying, I guess I should say, because we get the n factorial to cancel. In the top of the fraction, we have another n plus 1, and in the bottom we have an n plus 1, so those cancel, and now we're left with this ratio, and we can drop off the absolute value, because of course everything here would be positive. There's no alternating components to this infinite series. After that, what can we do? Well, it's kind of a trick we've been doing throughout chapter 9, but I guess before we get to that trick, what in the world is this limit equal to? I guess we'd have something like infinity to the infinity over an infinity to an infinity, which I guess could be maybe looked at as 1, but unfortunately it's not equal to 1. It's just some sort of crazy indeterminate form, and that's not the way we're going to approach this problem. We're going to need a very special limit that you're going to see for the first time in this class. So before we get to that special limit, what we can realize about this fraction is since the top and the bottom have a power of n, we can, for the lack of a better word, factor out that power of n, which would mean we'd have n plus 1 over n all to the n power. Again, that really doesn't help us much because we would, I guess, end up with some sort of infinity to the infinity power, which doesn't make any sense. But this is actually a special limit. This limit, without taking the time to prove this in this particular lesson, this limit is actually equal to the number e. Just to be thorough here, you could also see this limit kind of split by simplifying this fraction right here. Of course, n over n would be equal to 1, and then we'd have 1 over n as a separate fraction. So you can see it either of these ways, but bottom line is this special limit is equal to e. And now, of course, we can answer what this limit is equal to, and it's equal to e. That's kind of the whole limit process that we needed to kind of go over, but now we can go back to our ratio test. The result of this limit is equal to 2.7, which is what e is equal to, which is bigger than 1. And our conclusion based on the ratio test is that if we get a limit that's greater than 1, then we say that this series up here diverges, and again we have to state the test we used here, it's diverging by the ratio test. Okay, in this last slide we're going to take a look at this root test, and this is actually one slide that's being dedicated to this root test, mainly because, not that it's not important, but mostly because it's not really tested on the AP test. It's good to cover this to kind of get an overall picture of all of these tests, but it really doesn't appear on the AP test. It's just good to go over because it actually is connected to the ratio test in a sense. So what is this root test? Well, like the ratio test, the result of a limit we're going to take gives us actually the same conclusion. So kind of forgetting this for a second, kind of ignore that it's there. I'll explain that in a moment. If we take the limit of this thing and get a value less than 1, then just like the ratio test, we can say our infinite series converges absolutely. And then you can probably guess after that, if we take the limit of this thing, which again I'll talk about in a second, but if we take this limit and get a number bigger than 1, then we know our infinite series diverges. Just like the ratio test, if we get a limit equal to 1, the test was inconclusive. But really, just like the ratio test, it means you didn't apply the correct test. Really getting this inconclusive answer just means you should have never used the root test, just like with the ratio test. Okay, so then what is this thing that we're taking the limit of? Well, the reason this is called the root test, and maybe it should be called the nth root test, is what we're doing is we're taking the nth root of our infinite series with an absolute value. You'll kind of see that process as we go through an example, but that's the idea. We're taking the nth root of our infinite series as an absolute value. And then, of course, taking the limit of whatever we get when we do that. So then why are we taking the nth root? Or maybe more appropriately, the question we should ask is, how do you know when to use this root test? Well, the way I can kind of get you to see that is just realize that when we take the square root of x squared, that's of course just equal to x. In other words, the square root and the square kind of cancel each other out, and x is a lot simpler. Same thing with the cubic root. If I take a cubic root of x cubed, that of course is just equal to x. So how are you going to know when to apply this root test? The way you're going to know when you should be applying this root test is when you see stuff to the nth power, because if you were to take the nth root of that would of course make it much, much simpler. But the key is to see everything to an n power. If we had something that wasn't to an n power like you saw in that last slide, then of course the ratio test would be more appropriate to use. But here you'll notice we have the power to the nth power, we have the numerator to the nth power, and we have the denominator that has an nth power. So maybe taking the nth root of it using this root test would be the way to go. So that's what we're going to do. We're going to take the nth root. We're taking the limit, by the way. I'm ignoring that for a second. But we're taking the limit of the nth root of our infinite series. And again, we're also applying an absolute value to that. Okay, so that's kind of the setup. Once you realize how to set this up, really it's just a matter of simplifying and then taking the limit after that. So let's talk about the simplification. The reason we can cancel out that -1 to the n power is the reason we kind of discovered in 9.5 with the alternating series issue when we're trying to test for absolute convergence. When you take the absolute value of an alternating piece like you have in the top here, that of course cancels that piece out. So because of that, we're just left with 1 over n plus 1 all to the n power. Once we do that, we're kind of ready to go. If we take the nth root of everything, of course the nth root of 1, or any root of 1, is just 1. And if we take the nth root of the bottom, that power of n goes away. And that's why using this root test here was important. The one thing I kind of neglected to mention is why didn't we use the alternating series test here? Because it technically is an alternating series. The reason we didn't use the alternating series test is you would have had to have taken the limit as n approaches infinity of 1 over n plus 1 to the n power. And unfortunately, there's really no technique we've been given so far for doing a limit like that. So that's kind of why we didn't use our alternating series test here. But now you can see why the root test was a much better test to use. When we take the limit of this, we get 0, and as long as we get a number that's less than 1, we're going to be able to come to the conclusion that the series converges absolutely, and we got to, again, state the test we're using by the root test. Okay, again, here we have another example that's going to be a great candidate for this root test because both the top and the bottom of this fraction have a power of n. So what I'm going to do is kind of, again, it's not really the right way to say it, but for the lack of a better way of saying it, I'm going to factor out that power of n. So if I factor out that power of n for the numerator, well, it'll just be left with e squared. And of course in the bottom we're just left with n, and then all of that becomes the nth power. Okay, so I think we're ready now. The reason this is a great candidate for this root test is if we take the nth root, then that nth power goes away. The other thing I'm going to kind of do, just to kind of ignore this absolute value, you'll notice that here nothing's ever going to turn out to be negative. We don't have any alternating pieces, so we don't have to worry about the absolute value. We can just go ahead and plug that in and take the nth root of that. And again, luckily, like when we take the square root of an x squared, or if we take the cubic root of an x cubed, that root and that power cancel each other out, and we're just left with whatever's on the inside. So here we're trying to take the limit of e squared over n. Remember, e is 2.7 roughly, and if you square it, that's just another number. So we're really taking a number and dividing that by infinity. And of course, hopefully you remember that limit is equal to 0, and just like the first example, our result turned out to be less than 1. So the conclusion we can come to is that this infinite series up here converges absolutely. And again, the test we used here was the root test. So we're going to say that again, this series converges absolutely by the root test.